Hi, in this video, we want to look at princals. All right, so princals is a part of something called Gifi methods. So Gifi is the name of, or was the name of a manservant of Galton, who is a very prominent historical mathematician. So if you ever look at a Galton board, that gives you a good example of the binary distribution being approximated with normal distribution, which is really cool, really fun if you geek out on that kind of stuff like I do. Galton is that guy. Well, Gifi is the name of his servants. All right, so that's completely unrelated to the video, topic-wise, really. But so what we want to look at is princals. So we're in the situation that I want principal component analysis, but I don't have numeric data. I have either ordinal or nominal data. All right, this is most commonly used with ordinal data, such as Likert scale data. Okay, so what we're going to do, we're going to transform our data some way, shape, or form into interval data. Then we're going to run something similar to principal component analysis, and then we're going to proceed as if we had PCA all along. It's really our big game plan on this. This code is modified from modern psychometrics with R by Mayer. Here is the GitHub page for the code that I use. I've changed things up to emphasize some certain things. So this is a very good book. You should check it out. All right, so what I want to do, I've got some data coming in, and it's categorical or it's ordinal, and I want to do principal component analysis for the project I'm working on, but I can't. Now, the naive thing to do would be to, if I've got ordinal data, it would be to just accept the ordinal values in terms of like their rank, right? And that would work. And we'll run through an example like that. Now, something to think about, if you proceed that way, remember that you're taking ordinal data and you're converting it to another format, a format that is considered more informative. Okay, so some people are going to rail at this and resist against this if they understand what you're doing. Make sure you understand what your client wants from your analysis. If there's someone who has very strict views on data usage in this field, do not use this technique. All right, so what we're going to do, we're going to take the AST self-report scale data. So this is looking at, this is a survey of subjects in relation to wisdom. All right, now here, the structure of the survey puts things into 5 different categories. We have self-knowledge and integration, SI, peace of mind, PM, non-attachment, NA, and the ones we're going to focus on the most in this video is self-transcendence and presence in the here and now. Okay, so now let's go ahead and load the data. So it's coming from the MPsychoR package. And I'm going to go ahead and I use the help documentation to know which columns go to which category of variable. And I create sub data sets just so I have things organized. And then I create the sub matrix M that has just the self-transcendence and the presence in the here and now and growth information. I'm reducing it down just so it's a little bit easier to interpret what's going on. Now, the output for the stuff that we're going to be doing gets pretty wide, and there's a lot of stuff coming out. To make things a little bit cleaner, I went ahead and removed part of the column names just to truncate things down a little bit, make it a little bit cleaner. I use string manipulation to do that. All right, so now what we're going to do for my first example, I'm going to do 2 things. I'm going to show we get very similar results. Not quite the same, but close. What I'm going to do, I'm going to pretend that my ordinal data is numeric data, taking the face value. So here, the face value is 0, 1, 2, or 3. And what I'm going to do, principal component analysis. Then what I'm going to do, I'm going to use princals, where I tell princals to convert my ordinal data to numeric data with constant distance between levels. All right, and it's going to be, so that's going to be a linear transform in a sense. And so then I'm going to show you that we're really getting the same thing. All right, so here I'm using principal component analysis And I'm just pretending that I have interval data instead of ordinal data with this. Now, what I'm going to do to get, so I get the output, this is principal component analysis. I want to get the same thing using princals to like bridge the connection between the two. All right, so what we're going to do, how princals works is that it does splines on our data. And so when I do splines, I have control over where the knots are of the spline. So that's where we get a new submodel in our spline and the degree of the submodels. Okay, so to replicate the principal component analysis, what I'm going to do, I'm going to say that there's no interior knots and I'm going to go linear. What does that do? Okay, so I have one spline for the entire data set and it's going to be degree 1. That degree 1 is saying that we have constant distance between levels. Okay, so here the parameter that we're going to specify is no interior knots in this example. Other options is to do it at the quantiles. I could also do it at equally spaced knots if I want equal spacing, or I could do it at the data points. And those are our options with this package. All right, so our splines are going to be straight lines to mimic PCA. All right, so here, my knots, I'm specifying with knots Gifi, which is in the Gifi package, that I want no interior knots. So that E means no interior knots up here. All right, so now I'm going to drop this into princals, and I'm going to specify degree 1. All right, degree 1 says I have a degree 1 spline between each knot, and there are no interior knots. Therefore, it's just a straight line over each of my ordinal data columns. Okay, so we get our outputs and we can see our loss value. So this tells me, this gives me an idea of fit, tells me the number of iterations. So remember, if it takes a lot of iterations for it to converge, that's a sign I have bad model fit with my data. Here, that's clearly not a problem. 25 is small. Here are our eigenvalues. So 2.6 and 1.4. And now I'm going to go ahead and plot something called the transplot. I'm just going to grab 4 different columns just so we can see what it looks like. And we can see that what's happening is that 0 is here, 1 is here, 2 is here, 3 is here. So the horizontal distance, the horizontal axis, are our original ordinal data. The vertical axis is our transformed values. Now you'll notice that if I go here to here, that is a vertical difference is the same as going from here to here vertically, same as going from here to here vertically. Okay, so really I don't need this line, I just need the actual points to look at. All right, so now I want to check to see, did I get the same results? All right, well, if I go through and I take the principal component analysis, take the standard deviation, square them, that's our variance estimates, I see that I get those eigenvalues. Huh. It's a Christmas miracle. All right, now I can take the evals from the princals output, and I see I get the same numbers. Oh, big surprise, right? All right, so now let's take a look at the loadings and the rotations. Okay, so it works out that princomps and princals use different standardizations, and therefore we get different loadings rotations. So princomp standardizes rotations to have Euclidean norm 1. All right, so here, remember that in principal component analysis, this is related to singular value decomposition. We like unitary vectors. All right, we want orthonormal. Okay, and then princals, it standardizes the rotations to correspond to those eigenvalues. So what it's doing is it rescales things to match the eigenvalues. That way we have more of a direct connection. So the variability connects to that variability measurement. All right, so here is the principal component analysis rotation. Now here are my loadings. Now at first glance, and this is just the head, this is just the first 6 rows. At first glance, these look very different. But if I take the princal loadings and I do some rescaling, oh, actually, oh, I'm getting ahead of myself. All right, so if I take the sum of squares on the principal components, I see I get 1, I get 1. That's because it's a normal vector for each of them. If I do the same thing on the loadings, I see that I've got those eigenvalues back. All right, so there's advantages and disadvantages both ways. If I want to have linked 1 vectors, the PR comp is a better choice. If I want princals, then I would definitely want, if I was using princals, I'm going to be probably using the eigenvalues. Either way, it's all good. So now if I go through and I rescale the loadings from princals, I'll notice I get the same values as the principal components up to a sign change. So if I multiply a vector by plus or minus 1, they're considered the same for this purpose. And so you notice I have 0.406, 0.4393. I go up here, I got 0.406, and then I got 0.4374. So it's pretty close, not quite the same, but it's pretty good. We'll allow a little bit of rounding off error. All right, so effectively we have the same thing just on different scales. All right, so now let's go through an example where we're going to work with ordinal data, and we're going to use default splines, default knots in a situation. All right, so default splines are at the data points, and we're going to be using a degree 2 quadratics. Okay, so this is more flexible than the one we looked at previously. All right, so when I go through, I can see that I've got my loss value. Here's my number of iterations. It's a more complicated model. It's a more flexible model, so it took more iterations to go through. And here are my eigenvalues. Okay. So now let's take a look at the transplot. When I look at the transplot, I see that I have these stair steps. Now, the thing to think about is not the stairs, it's the value at 0, value at 1, value at 2, value at 3. Okay, so I want to point out to you that this vertical difference is very different than this vertical difference. Here we're allowing a lot more flexibility in our ordinal data. So what it's doing is preserving the order, converting it to interval data, but the interval changes. So we do not have a constant difference between our levels. So here we're saying that look at the vertical difference. The vertical difference between 0 and 1 is very small. So we're saying the difference between 0 and 1 is not very great. When I looked at the difference between 2 and 3, that's a pretty big difference. And it's always relative to the other levels when we go through this process. All right, so now let's take a look at the factors that we get back. So we can treat these factors the same way as we do regular old factors first 2. There's a difference here. In this situation, like the second factor depends linearly on the first one, and the third depends on the first 2, and the fourth depends on the first 3, and so on. Therefore, we need to interpret these differently. These are different than like regular principal components. All right, so now let's take a look at our actual transform data. So here, I'm just going to take a look at the first 5 columns, and I can see this is the original data. Here is the transform values. And so these look very different. These correspond to the plots that we looked at a moment ago. So here, this is a better representation of the data if we want to treat these levels as interval instead of ordinal data. And of course, we can get our loadings plots. All right, when I look at this loading plot, first thing I look at is the first component. All right, the first component, everything's pointed in the same direction. So I interpret the first component as being like overall wisdom. Now, something to realize is that up to a sign change, it doesn't matter. So it's okay if it goes this way or that way. If I reflect everything over the vertical axis, that's okay. I get the same interpretation. And so the first component, let's go ahead and call that overall wisdom. The farther to the left I see an arrow, the more that column contributes to the overall wisdom factor. Now, second component, what that's doing, we can see that we have some up top, some down low. What this is doing to a large extent, this is detecting the difference between the ST and the PG data. All right, so if I look up here, the higher up the arrow, the stronger that column contributes to the second component. All right, so I see PG, 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 and a little bit of ST floating around, and all ST down here. So I conclude that the second component is separating out the difference between the two types of wisdom. All right, well, let's do another plot. Let's look at a scree plot. So this gives me an idea of, do I have enough components? Remember, in a scree plot, we're looking for an elbow. And so I can see that after I get past 2, things kind of flatten out. I hit diminishing returns. And so this elbow here at 2 shows that 2 is a good place to stop. Now, this also shows how much information am I losing by stopping at 2, but I'm satisfied with this. All right, so let's do this again. Now, this time, what I want to do, I'm going to incorporate row sums from the other types of wisdom questions. So here, we're going to take the other 3 types of questions that we have. We're going to take the row sums, and then we're going to put these in. Now, something about this, I have individual columns for ST and PG. I have row sums for SI, PM, and A, as is how each individual question from ST-PG was much influenced as all questions in SI, all questions in PM, and all questions in A, correspondingly out of the box. And so I'm not 100% comfortable with that. So what I'm going to do is I'm going to go ahead and say, you know what? I don't want internal linear stuff for the row sums, but I'm going to take data points for my splines on the individual questions. And we're going to go degree 1. And so I'm just running through princals. I'm just specifying 3 dimensions. And so now let's go ahead and take a look. Okay, now when I do it this way, we can see that all the STs that were up here now have come down, and the row sums are all up top. So to me, this tells me that PG is performing overall more similar to SI, PM, NA than ST. Now, this one PG question is a little bit on the low part, but I think that's okay for this situation. And so the first principal component, I consider it the same interpretation, that has overall wisdom, while the second component gives me information about the difference between the different classifications of wisdoms. All right, well, that's all I've got for you. Take care and goodbye.